Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you today about function notation. In this presentation, you'll learn function notation, and you'll learn how to evaluate a function to find function values. Function notation is a special notation used when a set of ordered pairs satisfies the definition of a function. Function notation is f parentheses x. We read this as f of x, and this notation replaces our use of the variable y in our equations. So that is, f of x and y are really the same quantity. They're referring to the same variable or value. The use of the letter f is not important in this function notation. You'll see often examples of g of x, h of x, p of x, a of x, so on. We really can use any letter. It is more so the use of this notation in the context of a function that makes it special. We use this function notation a few ways. One is to communicate an ordered pair relationship. For example, if we say f of 3 equals 4, then we're saying that when x is 3, y is 4. Remember that notation, f of x. So this is the y value for a given x. That means that the ordered pair 3, 4 would be on the graph of f of x as well. We also use this function notation to write the equation of a function. Since the y value and f of x are really the same thing, when we determine that we have a function like we did with y equals 3x plus 1 in our previous presentation, we can just replace that y value with f of x. That indicates that we are indeed talking about a function. We can also use this notation to name the graph of a function. So below I have a graph. It happens to satisfy the definition of function. So we could say that this is the graph of f of x, or sometimes we say for short the graph of f. In applied scenarios and even in just mathematical scenarios, we're often interested in finding function values. And so we'll do this here in context to start out. We'll look at Martha, who works at Carpets Incorporated, and she uses the function c of x equals 20 plus 7.5x to determine the cost, which we're representing with the function notation c of x, for purchasing x square feet of carpet. Some questions we might ask here in this scenario is how much will it cost to purchase 100 square feet of carpet? How much will it cost to purchase 1,500 square feet of carpet? And if Johnny has budgeted $1,300 for carpet, how much carpet can he buy? Well, in part A, we want to know the cost to purchase 100 square feet of carpet. Keeping in mind that x in this case is representing the square feet, we would simply let x equal 100 in our cost function. So c of 100 is 20 plus 7.5 times x. In this case, again, we're letting x be 100. And so this is 20 plus 750, which is $770. So the cost will be $770 to purchase 100 square feet of carpet. If we were looking at the graph of our function c of x, we would know that the ordered pair 100, 770 should be on our graph. In part B, we want to know the cost to purchase 1,500 square feet of carpet. And so again, we'll let x equal 1,500. In function notation, this is finding c of 1,500. And again, that's just simply letting x equal 1,500. When we do that, we find that the cost for purchasing 1,500 square feet of carpet is $11,270. And similarly, we would know that we would have the ordered pair 1,500, comma, $11,270 on the graph of C of X. In part C, we want to know how much carpet Johnny can buy given that he has $1,300. So in this case, we actually have a cost, and we're wanting to find X. So we would let C of X equal 1,300. And we do that here on the left side of our function's equation. And this creates an equation that we can solve. So we'll subtract 20 on both sides of the equation, as well as divide both sides by 7.5. That results in X having a value of 170 2/3. And so Johnny can purchase 170 2/3 square feet of carpet with the $1,300 that he has. This would tell us the ordered pair 170 2/3, comma 1,300 is an ordered pair that we would see on the graph of C of X. Consider the function f of x equals 2x over x minus 1. We'll find the following function values: f of 0, f of 1, f of 2, and f of -3. To find f of 0, again, this function notation, that's telling us that x is 0, and so we'll plug in a 0 for x. When we do this, we get the value 0, so f of 0 is 0. When we look at f of 1, again, that notation is telling us that x is going to have a value of 1, and so everywhere there's an x, we let x equal 1. But in this case, when we do that, we get 2 divided by 0. And 2 divided by 0 is an undefined value. Division by 0 is undefined. So in this case, we would say there's not a y value paired with x equals 1. There's no function value here. To find f of 2, similarly, we would let x be 2. And then we would just clean up and evaluate. We get 4, so f of 2 is 4. To find f of -3, we would do the same thing. Let x be -3. We would clean up and evaluate. So we would have f of -3 is 3/2. Again, it's important to note each time that we do this, we're finding ordered pairs. Like in this last example, we would have the ordered pair -3, 3/2. We should expect that to show up on the graph of f of x. Take a look here. We have a few ordered pairs plotted on this graph. Is this a function? If so, what is f of 4? Well, the graph is a function because every x value in the set of ordered pairs is paired with exactly one y value. We can toggle back and see that when x is 2, there's only one ordered pair. When x is, it appears to be 3, there's only one ordered pair. So on, so on, so on, and so on. So yes, it is a function. The second part, we were asked, what's f of 4? We'll toggle back here so we can find that. When we look at f of 4, we find the ordered pair here. We see that the y value associated with that is 9. So f of 4 is 9 because that is the y value that's paired with x equals 4.